Hi, today we are going to generate heat maps, and this heat maps highlights the most influenced region in an input image. So we will meet EigenCAM, a powerful tool for Yolov5, and we will understand how to provide insights within the Yolov5 and detect objects and also generate those heat maps. So we will start with an input image and understand how to do a simple object detection, and then we will create a heat map that focused on the specific area that is relevant for this object detection. Okay, so let's start with the installation part. I will not do a full detailed installation, since you can find the full installation on this video. I will leave a link here in the upper corner so you can download and follow the full installation. This specific video tutorial is deal with Yolov5 segmentation. However, all the installation process is basically the same. So I will leave a link for this tutorial. I also will leave an installation txt file, and you can see the first line in this installation file, name install.txt, points to this video tutorial. But let's cover quickly all the process. First of all, let's create a conda environment. Let's name it Yolov5. It will be based on Python 3.8, and of course we will activate this environment. Then we will choose a folder, and we basically would clone the Yolov5 repository as a subfolder under our folder. We can use I basically will use a tutorial folder, but you can choose whatever you like. Then we will clone the Yolov5 repository, and the next process is choosing which version of PyTorch you should install in your local machine. So in order to do that, you should run this command, nvcc -version, and you can see what is your CUDA version. It should be something above 11. I'm using 11.8, but you can choose your own version. But it's really important, if we go to the PyTorch, let's find the PyTorch website, and if we go to all the install previous versions, you can see that the last one is 2.3, and this support 11.8. So if, for example, you have another CUDA version, let's go down for an earlier versions, and let's go down, for example, here, this PyTorch version 2.0.1 supports CUDA 11.7 and 11.8. So this would be the command in order to install it. Let's see another one. For example, if you have CUDA 11.6, you should install PyTorch 1.13.1. So this is the process. If I go back, I'm using 11.8, so I copy this command from the PyTorch website. Then you have to install a more relevant Python libraries that are required by the Yolov5, like GitPython, Matplotlib, NumPy, and it's really important that the version will be above those versions. As you can see, some of them are above, some of them are not. You are not required to a specific version. However, when you installing the Ultralytics version, it should be this version for Yolov5. Then you have to install OpenCV, but in order to do that, or before doing that, you should uninstall OpenCV headless, which is OpenCV without the visual functionality, and then reinstall the OpenCV with version above 4.1.1. So this is the installation part, and as I said earlier, you can follow my previous video that dealing with segmentation, but as I said earlier, the installation process is the same for segmentation and for object detection. Okay, let's continue to the next phase. So if you have done all the installation process, you should create a subfolder named Yolov5. Mine is under the main folder tutorials. So if I go inside the Yolov5, these are all the 5 that were cloned from the GitHub repository named Yolov5. Okay, before we start coding, it's very important that your home working folder should be Yolov5. That means that you have to click File, Open Folder, and choose the current folder where you install the Yolov5. As you can see, I installed it under Tutorials, Yolov5. So this is my home folder for Yolov5. Next, I have to choose the interpreter. So I click Control Shift and P and choose Select Interpreter and look for the right Conda environment. My Yolov5 environment named Yolov5 Tutorial, so it's very important that you should choose your current environment. Then we are ready to start the coding. So I will create a new Python file and let's call it EigenCAM.py. And the first command should be installing GradCam. So I just put the pip install GradCam, and you should install it on your current Yolov5 Conda environment. So you should go to your Conda environment. As you can see, I already activate the Yolov5 tutorial, which is my current Yolov5 Conda environment, and I should run this command, the pip install GradCam. Let's run it. Pip install GradCam. And as you can see, it's installing the GradCam Python library. Great. So now let's start coding. First of all, we will import the relevant Python libraries. We will import PyTorch, and also we will import OpenCV and NumPy. We will also import the EigenCAM from the PyTorch GradCam to create the class activation maps and a utility function to overlay the cam on the image. Great. Next, we will define colors as a NumPy array for random colors. This will be used to draw a bounding box around the selected objects. Now we are creating a new function named parseDetection. This function takes the detection results and extracts the bounding box, colors, and names of the detected object. So we will start with convert detection results to a pandas data frame and then to a dictionary for an easier manipulation. Next, we initialize an empty lists to store the bounding box, the colors, and the names of the selected or the detected objects. Then we will run a loop over each detection in the results. We will start inside the loop with retrieve the confidence score of our current detection, and if the confidence score is less than 0.4, we will skip this detection to ensure our accuracy. Then we extract the coordinates of the bounding box for each current detection. we will grab the x minimum and y minimum point, and also the y max and the x max and the y max points. Great. So let's continue to the next phase. Now we should get the name of the detected object. And after the name, we also need the category index of the detected object. Great. Next, we need to select the color for the bounding box based on our category index. Of course, it will be one of the random colors. And then we will append the bounding box coordinates, color, and the name to our respective lists. And after that, we are return the list of the bounding box, the colors, and the names. Now we generate another function. Let's call it draw detections. This function takes the bounding box color and names and draw them on the input image. We'll run a for loop through our input variables, and then we will grab the coordinates out of the current box, and then we will draw a bounding box around the detected object using the OpenCV rectangle function. As you can see, we are sending to the function several arguments like the image, the coordinates of where to put the rectangle, and the color and the thickness. Then we will put the label of the detected object above the bounding box. As you can see, our y minimum value is -5, means that it will be 5 pixels above our rectangle. Those functions are a common practice of using OpenCV. And at last, we will return our image that already contain our rectangles and labels. Now we run the image inference detection. First, we will load and pre-process the input image. We will read the image from a specific path. This would be our cow image. And next, we will resize it and create another copy of this image. So we are loading the image, and now we are resizing it to 640 by 640. Okay, next we will normalize the value by dividing it by 255 and keeping a float variable in the image values. Now we are transforming it to a tensor, and then we will prepare it for running it to the inference of Yolov5. Now we are loading the pre-trained Yolov5 model from the Torch Hub. This model is used for our object detection. And next we will print the model architecture just to double check that it was loaded correctly. So let's run it. And now, as you can see, we have all the architecture of our Yolov5 small model. we use the Yolov5, S mean the small architecture. Next, we will define the target layers for the EigenCAM. These are the layers from which we will extract the class activation maps. Then we will run the model on our input image to get the detection results, and let's print the results and see if it detects those cows in our image. Okay, as you can see, we found 3 cows and 1 horse. I believe that the confidence will take out these cows. So let's continue to the next step. And the next step would be parse the detection results to get the bounded box colors and names of the detected objects. And let's print those detected boxes and names. And let's see the results of our detection. I earlier made a syntax error. I have to replace it with xmin. Now it's okay. Let's run it. And now, as you can see, we have 3 cows, and those are the bounding boxes of those cows. Great, let's continue. So now we would like to draw the detections on the image and display the result. So we will use the function that we generated earlier, draw detection, and we will send the boxes, color, names, and our copy image to this function. And after that, the result of this function would be the image that containing all the detected information. So let's show this image. We're expecting to see an image with detections and labels. Great, as you can see, we have a cow with the labels and bounding boxes. Let's continue to the last phase. Now let's create our CAM model and run our image and detection through this CAM model. So we will move the results, move the model to a GPU for a faster computation. Next, we will create the EigenCAM object with the model and the target layers. Now we generate a class activation map for the input image and overlay the class activation map on the input image to highlight those important regions. So basically, now we are creating those heat maps. And now we would like to show this image that contains those heat maps. So let's run the result. Let's wait a few more seconds. Great, as you can see on the right side, it's the detection, and the left side is the heat maps. Great, you are most welcome to subscribe my channel. Thank you very much. Bye bye.